Exam first, because I know that's what is more important to you, and then we'll go over the deletion exercises. And I'm only going to go over the questions I know were widely missed. So I'm not going to go over question 1. It was widely, actually I'm going to go over 1B, 1C, because some of you missed 1C. So the size of the input is important even when considering big O notation. So for very small values of n, constants do matter. And in this case, the large constants for the second algorithm mean that for small values of n, such as n less than 50, algorithm 1 is preferable. And what I really needed was some computations, not just, oh, the constants are big for algorithm 2 and they're small for algorithm 1. That's not proof of anything. That's just hand waving it. Okay, so I needed some computations. You should be able to perform those computations without a calculator. I didn't need an exact computation. I just needed a ballpark computation. Okay, so 50 log n is somewhere between 5 and 6. So say 5, that makes 5 times 10,000, 50,000. So this is about 50,000 plus 10,000 is about 60,000. Versus here, 50 squared is about 2,500. Multiply that by 5, it's about 12,500. Doesn't come anywhere close to 66,000. So I told the TA to deduct a point if you got it right, but if you hand waved it by saying, well, the constants are big for algorithm 2 and they're small for algorithm 1. That's not precise enough. You need, again, we're trying to make you to where you argue effectively, not just hand wave things. But that was the only issue there. Number 2, a lot of issues with number 2. So we're going to go through that. And this is important because one of the important things about this course is knowing which data structure is the right one to choose because it impacts the efficiency of your programs. Okay? Choosing the most efficient data structure is important. So on the first one, where you're doing a distribution of exam scores by counting the number of exams in the range 0 to 9, 10 to 19, the best one is a vector. And what you should be doing is dividing by 10 when you are counting. So you actually only need a vector of size 10 here. Okay, maybe size 11 if you're worried about 100 mapping to something outside the vector. But the maximum size vector you need is 11. You simply divide each score by 10 using integer arithmetic, and it will give you the correct entry in the vector to increment. So this was definitely better than a hash table. Okay, even though both have order 1 time complexity, vectors are faster than hash tables. Okay, second one, you have a test bank of questions. You want to ensure the test taker has never presented the same question twice, and you store only the questions that the test taker has seen. You do not need to keep the questions in sorted order. That was an important thing here, because you do not need to keep the questions in sorted order. You do not need to use a set, because that is an order log n time data structure. Because you only need to be able to retrieve the question and insert it, a hash table is better. Those are order 1 operations. So the only time you really are supposed to use a map or a set is when order is important. Otherwise, a hash table is faster. Okay? On C, you're implementing a router for the internet which receives packets from various locations, transmits them to other locations. The important thing is, as the packets arrive, they're placed at the end of the line, and when they're removed from the front of the line. You want to use a double-ended queue for this. Okay? Yes, a list works, but it is not as efficient as a double-ended queue. Double-ended queues are specifically designed to implement what are called first in, first out lists, which is what this is. You insert things at the back, you remove them from the front. Doubly-ended queues were invented for this particular type of situation. You're implementing a diary, storing dates and locations. Okay? And the dates must be kept in chronological order. That eliminates a hash table. Okay? And a person may visit multiple locations on the same dates, which means you're going to have to use a multi-map. So the fact that you're storing key value pairs means you need a map. The fact that you're keeping them in chronological order means you need to use a map. If you weren't keeping them in chronological order, a hash table would work. But you're keeping them in chronological, meaning sorted order. There can be multiple pairs. You need a multi-map. Okay, next one. You want to reverse the lines in a file by storing the lines in the same order they're stored in the file, that is, adding them to the back of the data structure, and then traversing the data structure from back to front. That is perfect for a vector. When all you are doing is adding to the back, and then you're just traversing, vectors are perfect. Vectors are very efficient when you're only inserting at the back or removing at the back. Okay. You want to implement a to-do list. The person can add and delete items anywhere in the list. It's a list. Okay, that's the best data structure here. Yes?
Why isn't a deck good for the last one?
Why isn't what?
A deck, the one.
This one?
Yeah.
Vectors are faster. Okay, DQs would be the second best here.
Which operation, how is it faster?
Because you're only inserting at the back. DQs are optimized for insertion at the front and the back. But DQs are not as fast as vectors. Okay? When you're inserting just at the back, vectors are faster. Okay? DQs are not quite. So if I was inserting or removing at the front as well, then DQs would be the right answer. But here I'm only inserting at the back. Vectors are faster than DQs for that. Okay. Just a sec, let me get to the. So you're keeping track of the number of times that each IP address has been accessed or has accessed your website. So what you're keeping in effect are key value pairs, which is the IP address and the number of accesses. And you need to keep the IP addresses in sorted order so you can perform range queries. The IP addresses are unique. So the fact that they're key value pairs means you need a map or a hash table. The fact they're in sorted order means some kind of map. The fact that they're unique says a map, not a multi-set or multi-map. Okay, John, you had a.
For the list on the second one, since you're just inserting or adding and deleting arbitrary places, I didn't see anything mentioned like linking the items together besides just saying list. So why would
Okay, so you are. But I didn't say anything about having to look up the keys. It's more just adding and inserting items in arbitrary places in the list. And I'm specifically using the word list here. I'm not using the. It's, yeah, but when you have a to-do list, you have to think about this. A to-do list, you're going through a to-do list like that, okay? You're not looking up things in a to-do list. So I'm not, you have to think about the functionality too, okay? It's a to-do list. You go through a to-do list front to back. I'm not going to be swayed, I'm afraid. Okay, I understand where you're coming from, but you have to consider context, okay? Yeah, there is some kind of order to a to-do list that you care about, okay? Okay, other questions about this? I guarantee you, there's going to be a question like this on the final. This is one of the most important things you get out of this course, is that we are teaching you about data structures, and being able to select the right one given a problem and some constraints on the problem is really important. So I guarantee there will be a problem like this on the final. Yes?
So is the final a little bit cumulative?
Pardon?
Is the final a little cumulative?
So when the question was, is the final just a little bit cumulative? Remember, you're kind of getting implementations of trees and maps and recursion on this one. So it's, I guess, yes, it's a little bit cumulative in the fact that you still have to know all the data structures in the class, okay, and their running times. Okay, it's not going to be like implement a doubly linked list. That was the last one. So if there's any like implement this or implement that, it's going to be recursion or trees. But I do expect you to still know running times of data structures and when to use them. Okay, so that is the extent of the cumulativeness. Okay, other questions about number 2? Okay, y'all did well on 3, except I didn't do well on 3, because the answer to 3B is Brad, not Smiley. The funny thing is, I always run code to check the answers, and I'm not sure why this one is wrong. So I either modified something at the last minute or did something. So not sure what I did, but the answer there is Brad, not Smiley. Okay. 6 you all did for the most part well. Oh no, that is not true. How did we skip all the way? So 4 y'all did. Yes, you did well on 4. 5 presented a lot of problems. Almost none of you got full credit for 5. So we were saying that there were n, so I want to insert n telephone numbers into the following data structures. Whoops. So I want to insert n telephone numbers and then perform n finds. 1 for each telephone number. So 1 for each of the telephone numbers. It says give the total big O running times for the find and insert operations. And just to reinforce it, I say I do not want the running time for a single insert operation, but for all n insert operations. Despite that, many of you gave me the running time for a single operation. Okay? So I needed it for n operations. So for a map, the big O operation times for both insert and find for a single operation is log n. So if you perform n of them, you need to multiply log n by n. That gives you n log n as the total big O running times for your inserts and finds. For hash tables, the average running time is order 1. So if you perform n of them, n times 1 is n, you get order n for your inserts and finds. For a list, you are told to assume you are always inserting at the beginning. It doesn't actually matter whether you are inserting at the begin or end of the list. The individual time to insert at the beginning or end of the list is order 1. So it is order n total. But to search the list, you may have to, for a find, you may have to search the entire list, which is order n. So if you perform n of these operations, it's n times n or n squared. And finally, a vector. Since you are inserting at the beginning of the data structure, it is order n for a vector because you have to move every item that is right of that element, one element to the right. And since there's n elements in the vector, you have to move n of them. So each insert will take order n time, hence n of them will take n squared times. And just like with a list, you may have to search the entire vector for each of the items. If you're inserting at the beginning, they can't be in sorted order. If they were in sorted order, then you could do the search in log n time using binary search, and the running time would be n log n. But they're not in sorted order, so it's going to be order n for each find, n squared for n of them. Okay? So this is important when you're looking at the running times of algorithms. Not only do you need to know the running time for a single operation on a data structure, but you have to figure out how many times you are calling that operation on the data structure and multiply the two numbers together to get the total running time. Okay? And because we consider algorithm analysis on the last day of class, there will be algorithm analysis type questions on the final as well. Although there'll be more giving you pieces of code and asking you to tell me the running time. Okay, question 6. Most of you got that. The issue is a copy, and it's inefficient to be copying stuff. Look at the solutions if you're not sure what I'm talking about, since most of you got that. 7 was the last one that created a lot of issues for y'all. So here, this is a code reading problem, and you're given these 6 statements, and you're asked to figure out what happens with all the pointers. So statement 1 sets next node to be current node next. So current node next, this becomes next node. Statement 2 says current node previous is equal to current node previous. So that's current node. Current node that's current node previous, and hence current node previous is null. So this gets set to null by statement 2. So now statement 3 says current node next equals current node previous. Well, current node previous has been set to null, so this gets set to null. Then in statement 4, next node previous gets set to current node previous. Current node previous is null, so this thing gets set to null. Okay, statement 5 tries to say current node previous is null, and now it tries to go through that null pointer to get at that previous. We segfault right here because we're making an access through a null pointer. This returns null, so effectively what we're trying to do is null previous, and access through a null pointer gives us a segfault. Okay, this was designed to show you why it's bad to be using double pointers like this. The whole problem essentially boiled down to the fact that we used a double pointer there and it messed everything else up. Okay, so the solution, which I hope you also used in lab 8, is to add an additional temporary variable. So the whole problem was caused by the fact that I never stored or saved a pointer to the previous node, which was Ben. So in this simplified thing, I saved the pointer to previous node, and now everything, it's hard to do it side by side. Let me get a second window though, I'll try to do it. Show you what's going on. Okay, so here's, I can't quite get everything. Actually, maybe if I do it the other way, if I go here, I bring the other one over here. Nope, come on. Why do I keep getting... Oh, it is? Okay, thank you. Oh, I see what you're saying. Thank you. Okay, put this over here, this here, and no matter what I do, I can't quite get everything. Yeah. Okay, so here is the two codes. So basically, the current node previous, instead of setting it to current node previous previous, what I'm trying to do here is simply set it to the previous node's previous. So the previous node is Ben. I set it to previous because what I'm doing is Nancy is now, I'm trying to put, what am I trying to do? Put Ben, make sure I'm doing this right. Putting Ben between Nancy and, so I'm trying to put Ben between Nancy and Sarah. I can't do everything, I'm sorry. So I'm just going to have to kind of, so if I'm putting Ben between Nancy and Sarah, I'm going to have, I know how to do it. Okay, so I'm trying to put Ben here. So it means that Ben's previous is going to have to point to Nancy. So that's what I'm trying to do. Wait a minute. Yeah, just a sec. Let me back up. First thing I do is I need to set Nancy's next to be Ben. So the first thing I want to do is set Nancy's next to be Ben. Okay? So that's, since I have now a previous node, I can set current node next to be Ben. So previous node is Ben. Now I set current node's previous. So this is the previous. And it is going to point to whatever Ben pointed to. It turns out that Ben's node pointed to previous, but if Ben pointed to something else, I can't just set the current node previous to null. Even though here you can see that previous node's previous is null, in general, Ben would point to something else. So here we need to set Nancy's previous to whatever Ben's previous was. Okay? Then we need to make Ben point to Sarah. And the way we do that is by setting previous node next to next node. And we set Ben's previous. Ben's going here. Ben's previous needs to point back to Nancy. Nancy is current node, so we set previous node previous to current node. And finally, we have to set Sarah to point back to Ben, so next node previous equals previous node. So basically, the idea is you have to create pointers to each of the nodes that you're manipulating. And the two nodes you're also manipulating are the next node in the sequence and the previous node in the sequence. Okay, so it makes your life a lot easier to avoid those double pointer traversals. Yes?
What if we did the same thing but just out of order?
As long as it worked. If you have something you think works and you got points taken off, show me and I'll take a look at it. It doesn't have to be in that order as long as the order works. Okay. Okay, other questions about that? Okay, and then most of you did fine on problem 7, so I'm not going to go over problem 7. If you have questions about it, catch me after class. Okay? So, I know that the exam results weren't quite as good as they were for the first exam, but they're still quite good historically, meaning the way you performed on this exam is definitely in line with how students have done historically. The 88 median on the coding part was extremely good historically. The median on this was 65 out of 82. So it was roughly 80%, and that's historically what it tends to come in at. Okay, so median was a 65, so half the class was above 65, half was below 65. Okay, so need to finish up with binary search trees today and just show you some code, but also just want to quickly go over the answers to these because I guarantee you there will be delete questions about binary search trees on the final. So the first one you were asked, by the way, here's what I also guarantee you on the final. You will not be deleting leaves. Ah, bummer. Okay? Leaves are easy. Okay, you just delete them. So John illustrates our second case with delete, which is when you have one child. When you have one child, you promote that child and replace the deleted node with that child. So this is very simple. You replace John with Jill. And I am fond of very bad puns. I do wish I had Jack there, but for Jack and Jill, but I did not. Okay. Although I'm close, because Jack is a nickname for John. If you don't believe me, think of our president, John F. Kennedy, who I believe also went by the name Jack, if I'm not mistaken. But you can correct me if I'm wrong. Okay. So, next one. I said start from scratch and delete Laura. Okay, if we delete Laura, we have the dreaded two-child case. Guess what? That's the most likely case to show up on the final. So we find the largest node in the left subtree. The largest node in the left subtree is John. So we actually delete John, again, replacing John with Jill. And then we replace the deleted key Laura with the biggest tree in Laura's left subtree, which is John. And there we have the solution. Okay, just like I believe, I see some people taking pictures, but take that picture. I believe the correct answer is also on this slide because I also said delete Laura, so here's the correct solution too. So it is on the slide. And this is, you can get to it, it's just in the next assignment. So for November 20th, 27th, and 29th, BS tree deletion and ABL rotation exercises. Okay, and then I asked you to delete Brad. Okay, it so happens that, again, the biggest value in Brad's right, the biggest value now is what? Alfred. So we end up deleting Alfred, and Brad gets replaced with Alfred. So that would be the situation if I deleted brat. So questions about delete? Yes. Pardon? So the question is, what happens if the left tree is empty and we delete the root? I have an example. So if we go to the notes, Dr. Planck's notes, here it is. If we delete Binky, so here it is. So we're deleting Binky, no left subtree, right? It's a one-child case. Okay, so we replace Binky with Fred. Okay, so it's just a promotion to the, it's a one-child case. But I know it's not clear, obvious when you first think about it, but it's a one-child case. Okay, so we're all good with doing deletions? Feel comfortable with that? Feel like that's a certain, 5, 6, 7 points on the final? Well, if you're not sure, go back and do those exercises, and the sample final has deletion on it, so make sure you practice it. Okay, we need to do some code though. So find is pretty simple. In fact, we can find as part of our insert. So we're going to be going over some code about how we do things. So just like with lists, we have two data structures for our implementation. We have the actual nodes themselves, and you'll see that we have left and right pointers to our left and right children. We have a parent pointer to our parent, and then we have our key value pairs. And Dr. Planck is using a void star here. This is probably the first time you've seen a void star. You've seen voids, you haven't seen void stars. A void star is a generic pointer. So another way to think of it is an untyped pointer. So normally pointers are typed. So this is a void star is an untyped pointer, which means you can assign any pointer you wish to a void star because it's untyped. Okay, that makes it handy if we want to store a pointer of an unknown type. So here he's trying to make his tree as general as possible. So by using void stars, he makes his tree as general as possible. Now, the STL makes it even more general by using templates. But in this class, we don't go over how templates get implemented. They turn out to be a pain in the neck to implement. So we don't want to show you how that's done. Therefore, the next best thing we can do to make things as general as possible is to allow our value to be a void star. Now, that does have a restriction that the STL does not have. What do you think that restriction is? What kind of values cannot apparently be stored here? There are some types that cannot be, some types of values that we cannot store with a void star. User classes, we can store pointers to user classes, but not the user classes themselves, so that's correct. But there's some even more, generally we would be okay with storing pointers to user classes, so that's not a huge restriction here. Okay, normally we're not going to store actual stack allocated objects. We're normally going to store pointers to heap allocated objects. But there's another kind of values that we do commonly store. Strings can't be stored here, correct. We need a pointer to a string, so that's a good example. String was a good example. Come on, some more. Types that, primitive types. Any kind of primitive type, bool, char, int, float, double. You can't store any of those because we require a pointer. Okay, that's why this is not as general as the STLs. The STL can store both primitive types and pointers to elements, as well as being able to store so-called stack allocated objects. So, void star, get used to seeing them. So you can assign something. If I have something like, say, a person star, and I have a void star v, I can say v equals p, and there's no problem because I can always assign a signed or a typed pointer to an untyped pointer. It's just like when I can always lose precision, just like I'm allowed to say int x double y. I'm always allowed to assign an int to a double because there's no loss of precision. But I cannot say x equals y. What happens if I try to say x equals y? It's not overflow. It's a possible loss of precision, and the compiler will complain about it. It will give you an error message. Okay, the way you can stop that is by saying x equals int y, and then the compiler will happily do the conversion and assign the integer result. Okay, so the same thing applies here. If you do the reverse case and try to assign v to p, the compiler will complain. Okay, just a second. Okay, the compiler will complain because this is a loss of precision in some sense. Okay, it's not sure because you can store any, v could be pointing to anything. The compiler wants assurances from you that you know that it is pointing to a person star. So again, you can do the cast and then it will happily assign the pointer from v to p. But the compiler wants to be certain that you understand what you are doing. So you can always lose precision by assigning a typed pointer to a void star, but you can't go in the opposite direction. And the situation is analogous to ints and doubles. Okay? Yes?
I was going to ask, can you still dereference the void star pointer?
No. The question was, can you dereference the void star pointer? And the answer is no, because you don't know the type. So you could, if you wanted to dereference it, you would first you could do it this way. You could say person star v. That would be how you dereference it. So you would first cast it to a person star so it knows what type it is trying to dereference. Because without knowing what the type of v is, it's impossible for it to dereference it because it doesn't know. It can get to the memory, but C++ doesn't store the type of that memory. So it gets to the first bytes of the memory, but it has no idea how to interpret the memory because it has no idea what the type of that memory is. So if you simply say star v, while it can get to the memory, it has no idea what the type of that memory is. This isn't Java. Java would store the type of the memory with it, but C++ doesn't. So it has no way, once it reaches that memory, of knowing what it's pointing to. Okay? So it can't dereference. If you try to dereference it with star v, you will get a compiler error. Yes?
So can you say like v equals ampersand x?
Yes.
Okay.
So I can say v equals ampersand x for the same reason, which is it knows the type of x. It's fine with fine with losing precision. Okay, it's fine with losing precision. So it can take it's got the address of x. It's just storing. A pointer is a pointer. It's a memory address. Okay, so void star is fine with storing any type of memory address you feed it. It can take null. It can take 0. So on and so forth. Other questions about void star? Okay. So, then we have our container class. which contains the tree and contains our API. So we have insert, find, and delete. Should be no surprise because those are the three operations we focused on all semester. You'll notice that find returns a void star because that is the type of the value. And then you would downcast it to whatever specific type you want it. And the insert takes a void star. Dr. Planck claims in his notes that you have to cast that when you call insert, you have to explicitly say what you have to cast to a void star. I have never seen that. Okay, again, you're going from a specific type to a general type. You shouldn't have to cast when you pass the argument in. By contrast, when you take it out, you will have to. When you unpack it, you will have to downcast. Okay, then we want to be able to return a vector of the sorted values. Okay, so this is by keys. So we're sorting by keys and returning all the values, not the keys, but all the values associated with those keys. So as with doubly linked lists, our implementation is going to use a Sentinel node, which is again different from the book's implementation. We will keep the size, and this vector is simply meant to keep, is a temporary vector that is going to prevent us from always having to allocate and deallocate a vector when we want to get sorted values. And then we have some helper functions that are going to help us with doing some of our recursive calls, like when we want to print or make the sorted array, or when we want to destroy the tree. Okay, so for insert, so the idea is we have a sentinel, and that sentinel points to the root. And we're going to assume that the right child, the sentinel's right child, always points to the root. And then here's our tree. This is our tree right here. So these are our three tree nodes. So everything in yellow is tree nodes. The things in green are the pointers to the values. So the green objects are values. The yellow objects are our tree nodes. So the left, this points down here. The right, it points down here. These two are leaf nodes. So this is a leaf. This is a leaf. And their left and rights point back to the sentinel node. So if I was to make this a little clearer what's going on, this is effectively our tree. This is our sentinel node. I'll put a big X to indicate the sentinel node. Our left and our right children point back to the sentinel node. So we have only one sentinel node. The leaves, their left and right children, point to the sentinel node. The right child of the sentinel node points to the root of the tree. If we had this situation where the final one had a right child, okay, notice the left child, there is no left child, so it still points to a sentinel node. So anytime you do not have a child, you will point to the sentinel node. So only one sentinel node. So the way we know when we've reached a leaf is its left and right children will be pointers to the sentinel node. Okay, so here's our find. Very simple. We start by, we're not going to use recursion in this case. We're simply going to be going left or right till we find our node. So we start by getting the root of the tree. So this gets the root of the tree. Get the tree's root. And then, while true, if we're equal to the sentinel node, we failed. we fell out of the tree. So if we get to a leaf and we will continue to the sentinel node, and that's we've fallen out of the bottom of the tree. It means we did not find the key in the tree. Otherwise, if the string we are searching for equals the key at the current node, that is success, so we return the value at that node. Otherwise, if S is less than the current key, we go to the left by assigning it the left child. Otherwise, we assign it the right child. Questions about this find? Very simple. Today's after class activity is to try to write this find function recursively, because you can also do it by recursively visiting the left or right children. So you have to figure out what are your base cases. Your base cases are right here for you, by the way. You should be able to identify your recursive base cases. There are 2 of them. Okay. So this has all the information you need in order to do the after class problem for today. So you can implement it recursively. 2 of the cases you see here are base cases. 2 cases are recursive cases. Those are your hints. Okay, looking at insert, little bit bigger. So the first thing we need to do in insert is find where to put the new node. So the first part of our insert is the same as with the find. We're finding where the node needs to go, and we're keeping track of the parent. So when we are done, we are going to hopefully hit the sentinel node. So in fact, we are going to go all the way to a sentinel node. If we don't reach the sentinel node, it means we have already found the key in the tree, and if we find the key in the tree, we return 0 because we don't want to replace an existing key. So the key cannot exist if we're going to insert it. So if the key does not exist, we're eventually going to get to the sentinel node, which is why we iterate until n is equal to the sentinel node. When we come out, n is actually going to be the sentinel node. The whole point of this loop is to have the parent available when we come out. When we come out of this loop, we want to know what will be the parent of the node we're going to insert. So every time before we update n as we go through this loop, we first save n into the parent, because now we are setting n to be one of the 2 children. Okay? This is me? Why would this be me? Okay. That would be my phone coming to life when it shouldn't. Okay. So we have this being the finding the parent. Now we come out and we are ready to create the node. So you'll notice that we do not create the node until we know that we have to create one. Otherwise, we would have to delete it if we were not inserting. So we actually put off creating the node till we actually know we have to create it. Then we check some things. We check to see if the parent is the sentinel node. So if the parent is the sentinel node, it means that the tree is empty. So that's a special case. That's the boundary case, and we set the sentinel's right to be equal to n. Otherwise, we check to see if the string is less than the parent's key, it should be the parent's left child. Otherwise, it should be the parent's right child. Okay, so that is the insert function. And then size plus plus, we increment the size by 1, and we turn 1 to indicate we succeeded. So the final thing we're going to do is delete. Okay, that's the hardest one. So with delete, what we're going to do, the first two cases are easy. We won't do them recursively. The third case with the two children, we will have to do recursively. So the first thing we do, we find the node. Okay, same code that we have been doing. If we don't find the node, then we are going to be returning. So if we get to the bottom and we haven't found it, we'll fall out of the bottom of the tree. So if the key's not in the tree, we fall out of the bottom. We set the, or we just return 0 to indicate the delete failed. There was no key. Otherwise, we have a pointer to the node that we want to delete, so we find the node's parent. Okay? And we now are looking at our three cases. So the first case we're going to look at is the case where it has no left child. So there's two cases where it has no left child. It has the situation where it is a right child or a situation where it's a leaf. Okay, so that's the check. If it has no left child, then what we're trying to find out is it a, we're checking the parent, is it a left node or is it a right node? Here it is a left node, but that's what this code is trying to figure out. Are we a left node or are we a right node? Okay, and because it's the one child case, no matter what, whether we have a right child or not, in some sense, we are safe in assigning the parent the right child. If the right child is empty, that's fine. The parent will get a pointer to the sentinel node. So no matter what, we can replace this node. This is the node we want to delete. We replace it with its right child. So we're making the parent now point down to the child. And if there is no child, so if this was the node to be deleted, and it had no right child, well, no problem, because n's right will return the sentinel node. So we're killing two birds with one stone here. We're killing, this is handling the case where we have, it's a leaf node, and it's handling the case where we have a right child. Okay, the next one, next case, is if we get here, we know that we had a left child. If the right child is the sentinel node, we know we have this situation right here. So this is n. We know that our right child is the sentinel node. We also know the left node must exist. Why do we know that the left node must exist in this case? Because I checked it right here. I could not possibly be down here if the left was empty. The only way I get here is the left is empty. So now what I need to do is promote the left child becomes me. So whatever the parent node is, that parent is now going to point to my left child. So if n is the left child right here, then we make n's left be the left child of the parent. Otherwise, we make n's child be the right child of the parent. And the other thing we have to do is adjust the parent pointer for the child. So n's left parent becomes n's parent. In both cases, we delete n and decrement size. One last thing, and I will let you go. So The final case is we have two children. If we get here, we have two children. So what we do, we first find the largest value in the left subtree. So we go to the left subtree. This is MLC, is maximum left child. From the left subtree, we go down the right children until we find a non-existent right child. At that point, we know that MLC is the largest child in the left subtree. Hold on, this is important because if you mess this up in Lab 10, you will be unhappy. We have to save the values from the node we are going to delete. Then we delete that node, which is the largest key in the left subtree. So we recursively call delete. When we return, we can no longer access MLC. That's why we had to store the values of MLC into temporary variables. If you try to here say n key equals MLC key, it may well fail, and you'll wonder in Lab 10 why the heck it failed. So you need to make sure that you store the contents of MLC because it's going away. And finally, you replace the contents of N. One last thing, right here there is no delete. Notice I do not delete N. That's because I am deleting not N. N remains. What I am deleting is the node associated with the temporary key. So I actually did not delete node N. I simply replaced its contents. Okay? So I will let you all go.
So why can't you just do NP if you know that before you do it?
Good question. Which I did. The reason I can't assign it before that is I haven't called the week, right? Well, if I have already changed the values of 10, then I'm going to stop when I get to 10 and try to delete 10. Okay. Yeah, okay. Send me some email on that. Okay. No, I'm going to take actually, yeah, there's going to be so many of you. Let me take your. So if I'm going to have to take your exams if you got 3. I think that part in question 3 right. There's too many of you to take names. So what I'm going to do is take exams and I'll give the exams back. Actually, let me take names because I can't take. Remember, class. There's no class Tuesday or a week from Tuesday. Okay, so look at the video lecture. So I'll just take names here.